Dr. Jennifer Fraterrigo, University of Illinois.
I'm going to talk to you today about our project, which is focused on characterizing phosphorus hotspots and relating that to phosphorus loading to aquatic systems. We're interested in two aspects of phosphorus hotspots. Hotspots that are formed through natural processes due to microtopographic closed depressions. So these are areas in the landscape which are lower in position relative to other upland areas where phosphorus accumulates. We found in our previous research with Lowell Gentry and UGRI that soil phosphorus can build up over time, and higher levels of soil phosphorus then contribute to higher levels of phosphorus loading to tiles, drain tiles specifically, which then of course drain to surface waters, ditches, and then ultimately streams in the area. So our goal is to characterize these hotspots that are formed in microtopographic closed depressions. And the other aspect of hotspots that we've been studying are hotspots formed through land use history, specifically in areas where there have been abandoned farms and perhaps high manure inputs. We've also found elevated levels of soil phosphorus, which may persist for centuries, potentially, certainly decades. And also, again, because those leave signatures of high phosphorus in soils, they can contribute to high phosphorus loading to aquatic systems. Our research will accomplish two things. One is to quantify the amount of soil phosphorus across a range of topographic depressions, and also quantify the amount of phosphorus in areas where there were previously farms located which have subsequently been abandoned. And then the other thing that our research will accomplish is to link the soil phosphorus in these hotspots with the amount of phosphorus being delivered to tiles, in tile water, and then to ditches and streams eventually, to understand how those two relate. Our research is going to contribute to farmers' knowledge about understanding how much phosphorus is in their fields, and hopefully help them understand how they may more precisely apply phosphorus fertilizer in the future. So one way to think about this is that your typical test for soil phosphorus occurs as a regular grid of soil samples. However, what our research demonstrates is that that grid spacing may overlook these important hotspots which disproportionately contribute to phosphorus loss. So by understanding where these hotspots are located and how much phosphorus is in them, hopefully we can design sampling approaches that do a better job of really capturing that variability and characterizing the amount of phosphorus in the fields, which in turn can help farmers make decisions about where they may, for example, avoid adding additional phosphorus because there's already a sufficient amount available. We're using historical aerial photography to identify locations where there were farms in the past. So again, this could be 1930s, 1940s, 1950s era photography, and then we can look at more current imagery to understand where those farms have been abandoned, and that might indicate where we could expect to find some of these hotspots. The other thing I wanted to mention is in the Douglas County farm, we have instrumented tiles where we can automatically sample the tile water to look at the relationship between soil phosphorus in these hotspots and what is actually being transported from the fields into water bodies. We also think our work will contribute to improving information that can be used towards nutrient loss reduction, because we can more accurately characterize the amount of phosphorus that is being lost from these fields. That may help us to target areas where we need to increase mitigation efforts. We have relatively flat landscapes in this region, but that's why the microtopography is actually more important. So because it leads to these depressions, we can actually have erosion of soil occurring on this much smaller scale and leading to the accumulation of soil phosphorus. In other areas where there's more topographic relief, you may see erosional processes occurring, but at broader scales or larger scales. So the same idea of precision agriculture in terms of nitrogen application, I think we can adopt some of those same ideas here with respect to understanding where we might need to limit the amount of fertilizer applied because of these patterns in the landscape, these microtopographic depressions. So I think our work will absolutely contribute to improving efforts to have a more precise patterns of application and timing of fertilizer. Our work can contribute to improving the efforts to more precisely apply fertilizer, both in terms of the timing and the amounts. If we know where hotspots are located and can link that to previous land use or topographic patterns, then we can limit the amount of fertilizer being applied there and reduce the amount of waste that is potentially going to occur if we apply where there's already excess fertilizer available.